Hello, in this video I'm going to take you through limiting and excess reactant calculations, which is part of the higher chemistry course in the Unit 3 Chemistry and Society. So hopefully by the end of this video you will learn the meaning of a reactant being limiting or a reactant being in excess. We're going to explore some reasons behind making a reactant limiting, so why you would want to do that, and then also use mole calculations to show which reactant is limiting. So just to generally introduce limiting and excess reactants, if a reactant is limiting, that means it's going to limit the amount of product you're going to produce. So the reason it does this is because it eventually will run out before your other reactants do, which causes the reaction to stop. So once your limiting reactant has run out, the reaction stops and you don't make any more product, which is why it then limits how much product you make. It's an advantage to make a costly reactant or one that's maybe unsafe. So if it's a hazardous gas or a very reactive metal, it's a good idea when designing a process to make that reactant limiting, to make sure that it's completely used up, completely reacted, and therefore that helps to maximize safety and also improves profit if it's a costly reactant. Reactants that are in excess, you have an excess of them, you have more of them than you actually require, so they will not be completely used up and you will still have some of those reactants left at the end. Usually, when designing a chemical process, the reactants that are added in excess are the ones that are cheaper or safer to use, and what they then do is make sure your more expensive, unsafe reactants fully react, which helps you maximize profit and improve safety as well. So usually in any chemical process, there will be one reactant that's limiting and the others tend to be in excess, depending on how many other reactants you have. So we're going to have a look now at the calculations behind these and doing calculations to show which reactants are limiting and which are in excess. Usually in the SQA examination, it will tell you in the question which one's limiting, or it will tell you which one it's expecting to be in excess. And you have to show by calculation like the justification for that, but it's essentially the same thing, it's just the wording might be slightly different. So we're going to start off first of all by looking at ones where we're looking at limiting and excess reactants where they're both a solid mass. So my advice would be, as you read through the question, to write any numbers above the chemical formula related to where on the chemical it's related to. Just kind of helps you not get lost in the words of the question. So show by calculation which reactant is limiting when 20.2 grams of magnesium oxide. So here's the magnesium oxide over here. So I'm going to put 20.2 above that. And that's reacting with 20.5 grams of hydrogen sulfide. So 20.5 grams above the hydrogen sulfide. So because both reactants are solid masses, we're going to have to use the NM-GFM relationship for calculating the number of moles. Any time you're given both quantities of a reactant, so quantities of both reactants, you will need to do limiting and excess calculation before you go on to do any other form of calculation. So sometimes questions will ask how much product's produced. If you're given the quantities of both reactants, you will need to do a limiting and excess calculation first before you can then work out how much product you'd make. Because like mentioned earlier, it's the limiting reactant that will limit how much product you make. The one that's in excess, you can kind of ignore when you are calculating how much product you're making. So, however, this question is just identifying which is limiting, which is in excess. So if we put the numbers that we've been given in our mole relationship, okay, and then the GFM for magnesium oxide, so you'd add 1 mole of magnesium, which is 24.3, plus 1 mole of oxygen, which is 16, and that adds up to give you 40.3 grams. And then 1 mole of hydrogen sulfide would be 2 plus 32.1, which gives you 34.1 grams. So now we can calculate the number of moles for each of the reactants. So N is M over GFM. So if you were to do that for both of these, you would find that you have 0.5 moles of magnesium oxide and 0.6 moles of hydrogen sulfide. So now we know how much we have of each, but before we can conclude which one's limiting and which one's in excess, we need to apply it to the mole ratio. So this is where you look at the numbers that are in front of the chemicals in the balanced equation. So both of them have no number in front of them, which means that would be a 1-to-1 ratio. So if I write their formulas again, just so it's clear. So my advice would now be to cover up the reactant, like physically cover up the reactant on the right, and take the one on the left to decide how much of the other reactant you would then need to fully react your magnesium oxide. So if we have 0.5 moles of the magnesium oxide, based on the stoichiometric ratio in the equation, we would need 0.5 moles of hydrogen sulfide. So now that we know that information, it's pretty needed there, we can now compare to how much we've actually got. So if I take this block away, so we need 0.5, but we have 0.6, which means that the hydrogen sulfide is in excess. Okay, so you need 0.5, you have 0.6, which means you've got 0.1 moles in excess. Okay, so ideally, after you've done this calculation, you would then write a wee sentence just to fully explain your answer. So it would probably go along the lines of, as 0.5 mole of magnesium oxide requires only 0.5 mole of hydrogen sulfide, the magnesium oxide is limiting and the hydrogen sulfide is in excess by 0.1 mole. Okay. Writing your reasoning in a sentence just makes it very clear to whoever's marking your assessments that you understand which one's limiting and which one's in excess. Okay, so calculating how much you've got of the excess reactant helps enhance that explanation as well, but you could just have this information in a very well explained sentence without telling me how much is in excess, but it's a good idea to add that in if you can. Okay, so we'll look at another example now. So same process again. Show by calculation which reactant is limiting when 21 grams of nitrogen, so 21 grams above the nitrogen, reacts with 3 grams of hydrogen, just 3 grams above here. So again, both solid masses, so NMGFM. So the gram formula mass of hydrogen is 2 grams, nitrogen is 28, because that's 2 times 14. And then this has told us we've got 21 grams, this has told us we've got 3 grams. So if you use the N equals M over GFM relationship to work out the number of moles for both of these, you should find you have 0.75 moles of nitrogen and 1.5 moles of hydrogen. So now we're going to cover up the second reactant and use the mole ratio to work out how much hydrogen we would need to fully react all the nitrogen. So if we write this down here, so it's a 1:3 ratio this time. So if we want to react our 0.75 moles of nitrogen, we would need 3 times the amount of hydrogen. So we need to times that 0.75 by 3, which would give us 2.25 moles. That's how much we need. So how much have we actually got? Let's find out again. So we've got only 1.5 moles of hydrogen present, so that's not enough, which means that the hydrogen is now our limiting reactant. So what we can do now is use the ratio to work out how much nitrogen we would then react. So if we're going to fully react the hydrogen, because that's the limiting one, we're only going to need 1/3 of nitrogen, which a third of 1.5 is 0.5. So that's how much would react. Sorry, I'll move this over. So we should have 0.5 moles of N2 reacted, which means we would have 0.25 moles in excess, because we have 0.75 present. Okay, so then again you would write a sentence along the lines of, as 0.75 moles of N2 requires 2.25 mole of hydrogen, and there is only 1.5 mole of hydrogen. The H2 hydrogen is limiting, and the nitrogen is in excess by 0.25 mole. Okay, so that sentence really is just putting what you've done with the mole ratio situation here into words. So if you imagine you were trying to explain it to somebody who doesn't really understand what this mole ratio thing means. If we go on to another example. So this one's slightly different, but it's essentially just the same thing. So show by calculation which reactant is limiting when 6.57 grams of iron, so 6.57 grams of iron reacts with 500 centimeters cubed of 0.3 moles per litre acid. So our iron's a solid mass, which means we're going to use NMGFM. However, our hydrochloric acid is we're being given a volume and a concentration, which suggests we're going to need to use the NVC relationship for the number of moles instead. So the concentration is 0.3 moles per litre. Missed the extra L there, sorry. And then the volume, remember, you need to change to litres, so you need to divide that by 1,000, so that'd be 0.5 litres. And then the mass of iron, we've got 6.57 grams, and the gram formula mass that we've for iron is 55.8 grams. So for the number of moles of iron, we need to use N equals M over GFM, which is 6.57 divided by 55.8, 0.12 if I round it to 2 decimal places. And then for the number of moles when it's a solution, is C times V or V times C, it doesn't really matter which way around you put it. So that would be 0.5 times 0.3, which is 0.15. Okay, so again, I'm going to cover up the second reactant. So if we take our mole ratio, so it's a 1:3 ratio this time, again. So if we want to react all of our moles of iron, we need 3 times the amount of hydrochloric acid. So that'd be 0.36. Okay. How much do we have? The big reveal. We have 0.15 present, which is not enough. So that means, again, the hydrochloric acid is limiting, which means the amount of iron we're going to react is a third of that, because it's now a 3:1 ratio if we're working back the way. So we're going to react 0.05 mole of iron, okay, which means the amount we have in excess, if you do 0.12 take away 0.5, 0.05, sorry, is 0.07 mole in excess. Okay, so again, if we write our sentence as 0.12 mole of iron requires 0.36 mole of HCl, and there is only 0.15 mole HCl present. The HCl is limiting, and the iron is in excess by 0.07 mole. Okay, so it's exactly the same process, but you just have to use a different mole relationship to work out the number of moles of hydrochloric acid because it is a solution. We've got one more example, which again is slightly different. Sorry about the dogs, if you heard them. So this time we've got 0.7 grams of sodium, and we've got 700 centimeters cubed of chlorine gas, and then it's giving us a molar volume, which means we're going to need to use the molar volume relationship. So for the solid, N equals M equals and GFM equals. And then for the molar volume relationship, we've got N, V, and MV. If you've not come across the molar volume relationship yet, it's N equals V over MV, where V is the volume of the gas in litres, and MV is the molar volume in litres per mole. This can also be represented as one of the triangles, which is similar to the NMGFM one, but you replace the mass with the volume and the GFM with the molar volume. Okay, but the thing to remember is that that volume has to be in litres, much like the volume when it's to do with concentration. So if we've got 0.7 grams of sodium, the gram formula mass is 23. We've been told the molar volume is 24 litres per mole, and that means we need to change this volume into litres, so divided by 1,000 would give you 0.7 litres. So for the number of moles for the sodium, it would be M over GFM, which if we were to put in a calculator would give us 0.03 moles. And then for the number of moles when it's the molar volume relationship, that's V over MV, so 0.7 divided by 24, which would also give us 0.03 mole. So if we cover up the second one, take our mole ratio, so our sodium, our chlorine, it's a 2:1 ratio this time. So if we want to react all of our 0.03 moles of sodium, we only need half the amount of chlorine, so that would be 0.015. We need that many moles. How many do we have? We have 0.03. So that's more than we need, which means the sodium is limiting and the chlorine is in excess by 0.015 moles. You take those two away. So again, if you write your sentence as 0.03 mole of sodium requires 0.015 mole of Cl2, and there is 0.03 mole of Cl2 present. The sodium is limiting and the chlorine is in excess by 0.015 moles. And there you have it. Sorry if the writing got a bit scrappy there. So hopefully now you know what's meant by a reactant being limiting or in excess, that you can give examples of why you would make a reactant limiting. or give reasons of why you would make it limiting. You can also state that the limiting reactant will then go on and determine the quantity of product that's made, and that you can then also show by calculation which reactant is limiting or which reactant is in excess. Thank you very much.